Okay, this is going to be the second video on derivatives of power series. And if you haven't done it yet, I would watch the first video just to sort of catch you up on where we are. But what we'll do is almost the same thing we did in the last video. What I'd like to do is to find a power series for the function 1 divided by 1 plus x. Now, we've done this earlier in the course. This is one of the common Maclaurin series, so it should be in that common table that hopefully you already have memorized. But when we found it the first time, we did the full, long definition of a Taylor series. So we started with the original function, then to find the coefficients, you had to find the first derivative and the second derivative and the third derivative and so on. But you found all the derivatives, found the coefficients, and after a lot of work, you wound up with a power series for this. And what we want to do in this video is just show a quicker way of getting to it using the derivatives of another power series. Now, it's all based on the fact on this. If we look up here, the natural log of 1 plus x. And hopefully this is something that you remember that you've used throughout the whole course. The derivative with respect to x of the natural log of 1 plus x. And again, it's just the derivative of the natural log, it's just 1 over the argument. Well, the argument is 1 plus x. So the derivative of the natural log of 1 plus x gives you this. Now, 1 over 1 plus x is the function that we're interested in. We want a power series for that. So our approach will be just like in the last video. Since 1 over 1 plus x is the derivative of the natural log, we'll start with the natural log, find its derivative, then we'll have the power series for this one. So it's actually the same approach we did last time. So the first thing to do is to go and look up the power series for the natural log of 1 plus x, which is one of the common power series. So if you look it up, it should look like this. Now, you can get it in two forms. If it's in the expanded form, it looks like this. If it's in summation form, it looks like this. So it's got to be in one of those two forms. Now, maybe you want to get the final answer in expanded form. Maybe you want to get it in summation form. So just like in the last video, we'll do it both ways, and then you can have your choice of which way you want to go. So we'll divide it up into columns, and here's the original question. Here it is in expanded form, and in this column over here, it will be in summation form. So we'll follow the same approach that we did last time. So to begin with, just to write it down, what we want is the derivative of this thing. So we want to find the derivative with respect to x of the natural log of 1 plus x. So if we're going to find the derivative of the function, all you do is find the derivative of the power series. So we also want the derivative with respect to x, and you can just rewrite the power series right here. So originally it's x minus x squared divided by 2 plus x cubed divided by 3 minus x to the 4th divided by 4 plus, and so on, goes on forever. Then we also want to find, just like we've taken the derivative with respect to x and everything else, do the same thing here. So this time you want the derivative with respect to x of, and you can put this whole summation notation in here. So n equals 0 to infinity of, and then you've got minus 1 to the n times x to the n plus 1 divided by n plus 1, and then we'll put brackets around the whole thing. So in this step, it's just really a matter of setting it up to take the derivative of each part. So what this is going to give you, now just like in that last video, when you take the derivative of a power series, it's really what's called term-by-term differentiation. So just go term by term and take the derivative of each term. So the derivative of x is 1. Then, now using the power rule, the derivative of x squared would be 2x, but it's divided by 2. Then you've got plus, the derivative of x cubed would be 3x squared, using just the power rule, divided by 3. Then minus the derivative of x to the 4th would be 4x cubed, divided by 4, and it goes on forever. Now over here, when you take the derivative of this one, it'll give us a summation as n equals 0 to infinity, and we'll have this. Now, this is a constant, so you can just leave it alone. So minus 1 to the n power, and just apply the power rule to this. So take the exponent and bring it down in front. So the exponent right now is n plus 1. So we'll bring that exponent down in front. and it'll give us this. And the new exponent would be just this thing reduced by 1, which would now be to the n power. And then in the denominator, you've still got an n plus 1. We'll go ahead and put parentheses around that. So that's what it looks like if you do it in summation notation. Okay, now the last step is really just a matter of cleaning things up. The derivative of the natural log of x is, and you know from way up here, the derivative of the natural log is 1 plus x. So you know that this thing is going to be 1 over 1 plus x. And it's equal to, and now it's just a matter of simplifying things. Here's 1, then you've got a minus. Now here, the 2's will cancel out, which leaves you with an x here. And then in this next term, the 3's cancel out. So you just have plus x squared. In the next term, the 4's cancel out, which would give you minus x cubed plus and so on. So that's what the derivative would look like in the power series for that. Now over here, you'd get almost exactly the same thing, except that cancel out what you can. You have an n plus 1 in the top and the bottom. So the 2n plus 1's would cancel out. So the final summation form would look like this. N equals 0 to infinity. You've got minus 1 raised to the n power. And then x to the n. And you're done. So it actually turns out to be a pretty easy process. So again, if you use the derivative of a known power series to find a new power series, it really makes it a lot easier. And again, we did the same thing earlier. If you wanted to, you could use the full, long, formal definition of a Taylor series to get this. But really, by using derivatives, it makes the whole process much easier. So there's an example of using natural log. And let's do one more, just a kind of an interesting one here. And the second problem looks like this. Suppose you wanted to do this. Use a derivative of a power series for e to the x to show that the derivative of e to the x is e to the x. Now hopefully this is one where you might remember. So the derivative with respect to x of e to the x, it's an unusual function, and that the derivative of e to the x is its own derivative. So the derivative of e to the x is e to the x, but we would like to just quickly show that using power series. So again, we'll begin with the same thing. We'll start with the formal rule for e to the x, which is one of the common ones that you've done before. So if we put that up, it looks like this. So the power series for e to the x is this. Now, if we find the derivative of e to the x, it should be e to the x. So we'll do the same thing here, but we'll just do it in the form of a power series. So let's find the derivative with respect to x of e to the x. And hopefully we can show that that will turn out to be the original function. So this is going to be the derivative with respect to x of, and you can just rewrite this series. So 1 plus x squared divided by 2 factorial, x cubed divided by 3 factorial, and we'll put one more, x to the 4th divided by 4 factorial. And then it goes on forever. Okay, now in the next step, we'll actually go ahead and take the derivative. And again, when you take the derivative of a power series, it's called term-by-term differentiation. So just take the derivative of each term as if it was a separate problem. So the derivative of a constant is 0. The derivative of x is 1. Then the derivative of x squared would be 2x. And that's divided by 2 factorial. The derivative of x cubed would be 3x squared divided by 3 factorial. And we'll stick one more. This one would be 4x cubed divided by 4 factorial plus and so on. So what that's going to give you, that's going to give you the derivatives. Now, to simplify things, and I think I'll do this real quick, is it helps in simplifying them if you rewrite the factorials like this. I'm going to break out the first term of each one. So 2 factorial is like having 2 times 1 factorial. 3 factorial is like having 3 times 2 factorial. 4 factorial can be written as 4 times 3 factorial, and so on. So you can always break out the first term on each one of these. So we'll replace that, and we'll replace that with these things here. Now what that does, it gets you to this. First of all, the 0 disappears. Here's the 1. Then you can do this. This 2 will cancel out this 2, and it just leaves you with an x. An x over 1 factorial, but 1 factorial is 1. Here, the 3's cancel out, and you get x squared over 2 factorial over 2 factorial. Here, the 4's cancel out, and you get x cubed over 3 factorial, and it goes on forever. Now, hopefully, if you look at this power series and look up here at the first line, it's exactly the same thing as what it was to start with. So you found the derivative of e to the x, and it turned out to be this, but this is e to the x. So you showed that the derivative of e to the x is e to the x using power series. So kind of an interesting thing just to show you what it looks like. But again, whenever you find derivatives of power series, the whole key is just term-by-term differentiation. So it's like take the derivative of this term, the derivative of this term, the derivative of this term, and so on. And if you just do term-by-term differentiation, you can get the derivative of a power series. So in general, finding derivatives from power series is much easier than going through the whole the formal Taylor polynomial process. So there's a couple more examples of derivatives. Now in the next couple of videos, we'll look at integrals of power series.